Hello everyone, and welcome back to our Calculus 1 course. Today we are going over Intro to the Limit and Limit Properties practice problems. We've got about 15 questions today, so let's jump right into it and start working on some practice problems. So for our first problem here, we've got a piecewise function f of x, where if x is less than 1, then f of x is x squared minus 1, and if x is greater than or equal to 1, then f of x is 3x minus 1. We are looking at the point where a is equal to 1, and we are trying to find the left and right-handed limits, and then determine the limit as x approaches 1 of f of x. With these problems, I like to do it in two different ways. So the first way is we can graph the problem if it is a function that we know and can graph, and then the other way is going to be by writing a table and actually going through and plugging in numbers closer and closer to our value of a. So let's start with drawing a graph. So we've got a graph here, and let's call this top part blue and this bottom part red. So our first graph is a parabola which has moved down by 1 point. So it's going to look something like this until x equals 1, so until here. And in red, when x is greater than or equal to 1, then we've got a line with a negative slope, so it's going to look something like this. So from this, I can already determine that it seems like the limit as x approaches 1 of f of x does not exist. But before we get into that, let's just go ahead and plug in some numbers into a table to make sure that my graphing is right and we can determine for sure that the limit does not exist. So let's start with our left-handed side, and since we're going to a equals 1, I'm going to choose numbers that are around 1 and approach 1 from either side. So from the left-hand side, I'm going to choose x values that are slightly lower than 1. So let's start with 0, go to a half, 0.5, 0.9, 0.99, and one more just for good measure, 0.999. And for these problems, I would of course use a calculator. If you are not provided a calculator or not allowed to use a calculator, I would choose easier numbers to estimate and possibly just rely on my graphing ability. But let's say that we do have a calculator. If we go ahead and plug these into our blue equation up here, since we're approaching from the left-hand side, remember that means that we are tracing as we approach from the left-hand side to this point at 1. So at 0, we plug in f of x, we are going to get f of x is equal to negative 1. At a half, we are going to get negative 0.75. At 0.9, we are going to get negative 0.19. At 0.99, we are going to get negative 0.019. And at 0.999, we are going to end up with negative 0.0019. So it seems like from the left that we are approaching 0. These numbers are progressively getting smaller and smaller towards 0, which does align with what I'm expecting and seeing in our graph here. It looks like it is reaching 0 on that x-axis there. For our right-handed side, remember again, we're going to trace along this from a greater number towards 1 and see what we get at that point there. So once again, x, f of x, and now we want to be choosing numbers that are slightly larger than 1 and work our way down towards 1. So let's start out with 2 and go down to 1.5. We can go to 1.1, 1.01, and finally 1.001. So at 2, we are going to get 1. 1.5, we will end up with 1.5. For 1.1, we are going to get 1.9. 1.01, we're going to get 1.99. And for 1.001, we are going to get 1.999. So this one looks like it's gradually approaching 2. It's getting larger and larger each time that we get closer and closer to 1. And that again does seem pretty appropriate with what we have in our graph here. This is clearly higher than 0, what we got on our left-handed side. So for our left-handed limit here with the minus sign, we get that this is going to equal 0. That's what we're approaching. For our right-handed side, with the plus sign here in the superscript, this we're getting closer and closer to 2. We're getting very close to that number. And since the left and right-handed sides are not equal, then we can definitively say that the limit does not exist. For our second problem, we've got a similar problem here. We've got another piecewise function, so let's go ahead and start with a graph like we did. So I'm going to start with a graph here. In blue, in our first part here, we have x squared minus 4 over x minus 2. So these look like lines. These types of graphs, when you see them in this kind of form, they're usually lines of some sort with a hole where this x does not exist, right? So if we set this denominator equal to 0, we get x is equal to 2. These should be do not exist, right? Because it can't equal that at that point. We can't have 0 in the denominator. So this is going to look like a line with a hole at x is equal to 2. And since we're looking as x is less than 2, that means that our graph is going to look like something like a line with a hole or an open circle at 2. So we're going to get something that looks similar to this. And then our right-handed side here is just a constant at 5. So we're just going to have a line up here at 5. And we are looking at the point a is equal to 2. So once again, I am going to make a table. So for our left-handed side, once again, we are tracing along this line. I'm going to put my pencil down and trace up to the point A that we're looking at, and plug in some numbers here. Since we're looking at 2, I'm going to choose numbers that are close to 2 and gradually approaching that. So I'm going to start with 1, go to 1.5, 1.9, 1.99, and finally 1.999. And we get for our f of x, 1 is going to be 3, this is going to be 3.5, this is 3.9, 3.99, and finally 3.999. So we can see that these on the left hand are gradually going up towards 4. 3.999 is very close to 4. So I can say here that our left-handed limit is going to equal 4. On our right-handed side, we will do the same thing and choose numbers greater than 2 and trace along to get to a is equal to 2. So we get smaller, so let's start with 3 and work our way down. 2.5, 2.1, 2.01, and 2.001. For the first one, we're going to get 5. For 2.5, we're going to get 5. And these are all going to be 5 because this is just a constant. It's just a number. Every number is going to equal 5. So we're not approaching anything here. We just are 5, right? At x is equal to 2, this is going to equal 5. We didn't have to draw this table out, but just for consistency's sake, it's good to do that. But we can see that this is clearly going to equal 5 for our right-handed limit. And since our left and right-handed limits are different, we can say that the limit as x approaches 2 of f of x does not exist. Problem 3, we have another problem of this same style. So let's go ahead and draw our graph again here. In blue, for our left-handed side, we've got the absolute value of x. So remember, these are just v's of lines, and we're looking at x is less than 0. So this is just going to be a line. And for our right-handed side, we've got another line, 2x plus 1. So that is going to look something like this. And we're looking at a is equal to 0, so let's go ahead and write out our tables. For our left-handed limit, we've got x and f of x. And since we're looking at 0, I'm going to choose some numbers slightly less than 0. So let's start with -1, -0.5, -0.1, -0.01, and -0.001. getting closer and closer to a is equal to 0. And our f of x values are going to be 1, 0.5, 0.1, 0.01, and 0.001. So these are getting closer and closer to 0, which agrees with our graph. So we can say that our left-handed limit is going to be 0. And for our right-handed limit, let's go ahead and draw our table out. F of x, and choosing numbers that are slightly larger than 0 and getting smaller. So let's start with 1, go to 0.5, 0.1, 0.01, and 0.001. If we plug them in, we will get 3, 2, 1.2, 1.02, and 1.002. So these are gradually getting smaller and smaller towards a value of 1. So I can say that our right-handed limit is going to be 1. And once again, our left and right-handed limits are not equal to each other. We see that in the table and in our graph. So we can say that the limit as x approaches 0 of f of x does not exist. Our fourth problem here is the last one of this style. So last time here with these kinds of questions, I am going to graph. Coming from the left-handed side, we've got sine, and we're looking at a is equal to 0. So for sine, remember, that is going to be 0 at 0. So we're going to look something like this. And then we've got x over 2, so that is just a line. And it is going to look something like this with a line. So let's go ahead and draw our tables, our left-handed side, and choose some numbers that are slightly less than 0, getting closer. So let's choose -1, -0.5, -0.1, -0.01, and -0.001. If we plug these in for our sine function, we are going to get -0.84, -0.48. For -0.1, we are going to get -0.0998, and we're going to get -0.00999, and a bunch of 9s, 8, and finally here we're going to get -0.00099, and a bunch of 9s again. So these are gradually getting smaller and smaller, going towards 0. So I can say that our left-handed limit here will equal 0. And for our right-handed limit, let's go ahead and draw our table one last time for these. Choosing numbers slightly larger than 0, we can start with 1, 0.5, 0.1, 0.01, and 0.001. We plug these in, we are going to end up with 0.5, 0.25, 0.05, 0.005, and finally 0.0005. So these are also gradually getting smaller and smaller towards 0. So I can say that our right-handed limit is equal to 0. And now with both our graph and our tables here, we can see that these are getting closer and closer to 0. So in our graph, right, they're both ending up towards that origin point at 0, 0, and our left-handed side is 0, right-handed side is 0. So I can say that our limit as x approaches 0 of f of x is going to equal 0. So here we've got a similar problem to the last few, but this time instead of a piecewise function, we just have one full function, and we are once again finding the left and right-handed limits and determining the limit as a whole. So our function here is f of x is equal to the absolute value of x minus 2 divided by x minus 2. So with absolute values, right, we've got a negative part, negative x minus 2, and we've got a positive x minus 2. We see that we've got this divided by x minus 2 as well. So really what we're doing here is we're looking at positive and negative 1, because we can divide these and cancel them out, and we get 1 for our positive and negative 1. So our graph, if we go ahead and graph this out, what this is going to look like is we're going to have from one side negative 1, and the other side is going to be positive 1. So we can go ahead and check this with a table. So for our left hand side, right, we're going to do the same thing that we've been doing, x and f of x, get our table going, and we're looking at 2, so something slightly less than 2. Let's go with 1, 1.5, 1.9, 1.99, and 1.999. If we plug in, we're going to end up with negative 1 from the negative side. So this is going to be negative 1, negative 1, negative 1, negative 1, and negative 1. And for our right-handed side, same thing. Slightly larger than 2, so let's start with 3 and work our way down. 2.5, 2.1, 2.01, and 2.001. We go ahead and plug these in and solve. We will end up with positive 1 for each of these. And our graph and tables are aligning here, but our limits, our left and right-handed limits, are not aligning. So our limit, as x approaches 2 of f of x, does not exist. For our next question here, we've got f of x is equal to x squared minus 1 divided by x minus 1. So this is once again one of those questions that looks like a line with a hole at it, where the denominator is equal to 0, so this would be at 1. So let's go ahead and find our left and right-handed limits. If we look from the left-handed side, we get x and f of x, and we're looking at the point 1, so we need to find values slightly less than 1. So let's start with 0, 0.5, 0.9, 0.99, and 0.999. If we go ahead and plug these values in, we are going to end up with 1, 1.5, 1.9, 1.99, and 1.999. So these are gradually getting larger, getting very close to 2 here. So we can say that our left-hand limit is 2. From the right, we will do our table again, choosing numbers slightly larger than 1. So let's start with 2 and work our way down. So 2, 1.5, 1.1, 1.01, and 1.001. For our f of x, we will end up with 3, 2.5, 2.1, 2.01, and 2.001. So this is gradually getting lower and closer to 2. So our right-handed limit will be 2. And our tables and graph align here. It looks like we've got a hole at 2. Since our left and right-handed limits agree, our total limit will equal 2. And finally, this is our last question of these kinds of problems. We've got f of x is equal to 1 over x squared plus 1. So this function I don't really know off the top of my head. It's going to be hard for me to just graph it without knowing anything else or plugging in values. So let's just go ahead and plug in some values for our graph, and we'll figure out what our limits are. So for the left-handed side, we're looking as x approaches 0. So let's choose some values that are close to 0. So for the left-handed side, let's start with negative 1, negative 0.5, negative 0.1, negative 0.01, and negative 0.001. For f of x, we will get 0.5, 0.8, 0.99, 0.9999, and 0.999, and a bunch more 9s here. For our right-handed side, draw our table out, and we want to choose numbers slightly larger than 0 and go down. So we've got 1, 0.5, 0.1, 0.01, and 0.001. So for our f of x, we are going to get 0.5, 0.8, 0.99, 0.9999, and 0.999 with a bunch more 9s following. we've got our left and right-handed limits. Our left is getting gradually larger and larger to 1, and our right-handed limit is going gradually larger to 1 as well. So that means that our graph is going to look something like this, where we're going to start low towards 0 and work our way up towards 1. So it's going to look something like this, and then it's the same thing but mirrored on the right, so we start at high and then work our way lower. So that's a little bit of what this picture is going to look like, where the point up here is at 1, and that's what we see in our limits, where our left and right-handed limits are agreeing with each other, so our limit as x approaches 0 of f of x is equal to 1. Now we're moving on to some different types of problems here. We're looking at graphs and not any numbers here, so for these we're just going to do some drawing and figure out what our limits are. So for our first question here, we're looking at the point -3, and we want to find what does f of x equal, the left, right, and total limit look like. So let's go ahead and first look at what -3 is on this graph. So we've got -3 right here, and that is a solid dot. So at -3, our y is equal to -1, so f of x is -1. For our left-handed limit, we need to trace the graph from the left-handed side going towards our point, but as we can see here, there is no other graph at the point -3. So there's no way that we can actually approach x is equal to -3 from the left, which means that our left-handed limit does not exist. If we look at our right-handed limit, so coming from the right, we go ahead and trace towards our point. This is getting closer and closer to the point -1. And our left and right-handed limits don't agree, right? We've got one that does not exist and another that is -1, which means our full limit does not exist at -3. Moving on to our next point, we're looking at -2. So what does f of x equal at -2? Well, down here on the graph, we've got an open circle, so that is not what the point is equal to at that point, but we have this closed circle up here, which is at 3. So our f of x is 3 at x is equal to -2. For our left-handed limit, let's go ahead and trace from the left-handed side of this, going towards the point. We end up at 0, y is equal to 0. We do the same thing from the positive side, from the right-handed side, so tracing from here down to our point, and we get 0 as well. So since our left and right-handed limits agree, our total limit as x approaches -2 will also be 0. For -1, we've got a closed circle up here at y is equal to 1, so our f of x is 1. Let's go ahead and trace from our left-handed side. We're going to trace up towards our point, and we get closer to y is equal to 1. And same thing from our positive side. We're going to trace up the graph, and we get up to 1 again, and our left and right-handed limits agree, so our full limit as x approaches -1 will also be 1. And finally, for a is 2, we've got a closed circle at the top and a filled-in circle down here, which means that our f of x value is going to be this point here at y is equal to 2, so f of x is 2. From the left-handed side, let's go ahead and trace along our graph going up towards our point. We reach 4. And for our right-handed side, we're going to inch up closer, and we get 2. We're approaching 2. And our left and right-handed limits do not agree. Our left is 4, and our right is 2, so these don't agree, so our total limit as x approaches 2 does not exist. Here's another graph for us, so we're just going to do the same thing once again. So we're looking at a is equal to -3. So we've got this point here, which is an open circle, and we don't have any other circles on our graph here, so our f of x does not exist. Our left-handed limit, so let's go ahead and trace from the negative side, the left-handed side. We trace down. This is approaching 0. And for our right hand, we're going to trace up towards our point here. And our right-handed limit is going to equal 0. Since our left and right-handed limits agree, that means that the limit as x approaches -3 of this graph will also be 0. Let's look at -2 now. Once again, we've got an open circle and we don't have any points anywhere, so this f of x does not exist. Let's go ahead and find our left and right-handed limits. So the left-handed side from the negative, as we approach, we're going to reach -4. And our right-handed limit, we're going to approach from the right-handed side, and we once again approach -4 on the y. Our left and right-handed limits agree, so our limit as x approaches -2 will also be -4. For the point 0 here, we've got a closed circle, which tells us that it does exist at that point, and that is at 0. So f of x of 0 is 0. And for our left-handed limit, let's go ahead and trace our line, and we get closer and closer to that point at 0. Our right-handed line, same thing, trace the line, and we get lower and lower, closer to 0 once again. So our limit as x approaches 0 will be 0. And finally here for point 2, we've got an open circle at the bottom and a closed circle at the top, which means f of 2 is equal to 4, where that closed circle is. And let's trace for our left-handed side. From the left of our point, we go up towards 4. And for our right-handed side, we're going to trace our graph going down towards -2. So our left and right-handed limits here, they do not agree, so our limit as x approaches 2 does not exist. Alright, so now we are looking at some questions that are based off of the limit properties. So we've got 3 different limits here of functions. We've got f of x, which is equal to 2 as the limit of x approaches 4. For g of x as x approaches 4, we've got 8, and h of x is equal to 16. So let's go ahead and solve this limit here for a. We've got, let's write this out, we've got the limit as x approaches 4 of 3 times f of x plus 10 times h of x squared. So what's going on here is we've got this limit with a bunch of things going on to it, but we can actually go ahead and use our limit properties down here. So I see that we've got this plus sign between 2 functions. So here we can use our addition and subtraction rule, where if we're adding or subtracting 2 functions, we can actually go ahead and split them apart. So we can rewrite this as the limit as x approaches 4 of 3 times f of x plus the limit as x approaches 4 of 10 times h of x squared. Now we've got these constants that are sitting outside of our function, so we can go ahead and use our constant multiplication rule, which says that if we've got a constant c multiplied by a function, we can actually take that c and move it outside of the limit. So let's go ahead and do that. So we've got 3 times the limit as x approaches 4 of f of x plus 10 times the limit as x approaches 4 of h of x squared. And we can go ahead and split this apart one more time with our exponent rule down here, which says that if we've got a limit of a function raised to the power of n, we can move that limit inside the power, so our n can come outside and be surrounding the entire limit. So here we've got 3 times the limit as x approaches 4 of f of x. This stays the same. And here we've got 10, and now we've got this power of 2, which we can bring on the outside of our limit. So let's go ahead and write our limit as x approaches 4 of h of x, and this is all going to be to the power of 2. So now what we can do is we can look at what we were given here. So we've got the limit as x approaches 4 of f of x. We've got that right here. We've got the exact same thing here. So we can go ahead and just plug in our numbers as we were given them up in the problem. So this is going to be 3 multiplied by what we're substituting in here. So this can be substituted by a 2. So we can multiply this by 2. And now we've got plus 10 times whatever we have on the inside, which is h of x. which looks just like this. We can plug in our 16 here. So this is going to be 16, and now we're going to square that. So now we can go ahead and solve. We get 3 times 2 is 6, plus 10 times 16 squared, which is 2,560, and we go ahead and add. We get 2,566 as our final answer. So for all of these problems, rather than actually going ahead and splitting these apart like we did here by our limit property rules with writing limit a bunch of times, right, I can see for B, our next question, this is going to be a lot of writing, right, because we've got both a addition and subtraction rule in the denominator, but we do also have a quotient rule because we have a quotient. We've got a fraction going on. So we can write the limit of the top is over the limit of the bottom and go ahead and solve each of these. But what I see is that after we broke everything apart, we can see that our f of x here, what was written first, 3 times f of x, just becomes the limit as x approaches 4 of f of x. So we were able to just plug in a 2, which is what we were given, directly into our problem here. So rather than going ahead and breaking it all apart, right, we have this exact same setup, 3 times f of x plus 10 times h of x squared. So everything looks exactly the same, which means instead of going through and breaking things apart, we can just go ahead and plug in our numbers directly as we see them in the problem. So let's go ahead and do that for B. Let's label this as A. For B, we're going to do the same thing. So we've got 4 times g of x. Let's go ahead and plug in what g of x equals right away. So that's going to be 8. And this is divided by 3 times h of x, which is 16, minus f of x, which is 2. And now let's go ahead and solve. We get 4 times 8 is 32. 3 times 16 is 48, minus 2 is 46. So we can go ahead and simplify this down to 16 over 23. And for C, let's do that up here. C, we've got g of x and the square root of 4 times h of x. So remember here, square root is equal to the power of 1/2. So here we're just using another exponent rule, where instead of using a 2 like we did in A, we're using 1/2. So we can do the same thing and just write it in under that square root. So let's go ahead. We've got 8 for g of x times the square root of 4 times h of x, which is 16. So this is going to equal 8 times the square root of 64, which is equal to 8 times 8, and that is 64. So for this one, we've got f of x is equal to 3, g of x is 21, and h of x is 9 for the limits as x approaches 10. So let's work through our problems. We've got a here, we've got 2 times h of x, which is 9, divided by f of x plus h of x. And this is minus 3 times f of x divided by g of x. So we can go ahead and solve. We get 2 times 9 is 18 over 9 plus 3 is 12 minus 9 over 21. So we can reduce these fractions a little bit, and we get 3/2 minus 3/7. And now we can get common denominators. So 14. This is going to be 21 minus 6, so that will be 15/14. For B, we have f of x squared, so 3, let's write that in blue. 3 squared minus 10 times h of x divided by 3 times f of x. And this is all multiplied by 6 times g of x, 21, minus 3 times h of x. So we can go ahead and start solving. We get 3 squared is 9 minus 90 over 9 times 6 times 21 is 126 minus 27. So this is going to equal negative 9 times 99, which is equal to negative 891. And for C, we have h of x squared, so that's 9 squared times the square root of 7 times g of x divided by f of x. So we go ahead and solve. We can get 9 squared is 81. And let's cancel out the 3 times 7 in the 21. So we're left with here 7 times 7, or 7 squared. So this is going to be 81 times 7, which is equal to 567. The next question, we've got f of x is equal to negative 1, g of x is equal to 6, and h of x is equal to 4 for our limits as x approaches negative 2. So for A, we've got 5 times f of x minus 3 times h of x plus 2 times g of x. So here we will get negative 5 minus 12 plus 12, so this is just equal to negative 5. For B, we have 2 times g of x plus h of x divided by h of x, 3 times h of x, 3 times 4 minus negative 1. So this is equal to 12 plus 4 over 12 plus 1, so that is 16 over 13. And finally for C, we've got g of x, which is 6 times the square root of h of x plus 12. So that is 6 times the square root of 16, which is 6 times 4, also known as 24. This one we've got f of x is equal to 2, g of x is equal to negative 5, and h of x is equal to 3. Let's go ahead and start plugging in our numbers. For A, we have h of x squared plus 4 times f of x divided by g of x minus h of x. So this is equal to 9 plus 8 over negative 8, which will be negative 17 over 8. For B, this one's a little bit longer. We've got 3 times g of x is negative 5 minus 2 times f of x times h of x, and that is divided by f of x plus h of x. So we can solve this. We get negative 15 minus 12 over 5. So this is negative 27 over 5. And finally for C, we have all of this squared, f of x, 2, minus h of x, which is 3, and that is going to be squared, and multiplied by the square root of g of x, negative 5, squared plus 1. Let's go ahead and solve. We get 2 minus 3 is negative 1. Negative 1 squared is 1, times the square root of 25 plus 1 is 26. So our answer here is square root of 26. Here we've got f of x is equal to 7, g of x is equal to 2, and h of x is equal to 5 for the limits as x approaches 0. So for A, we've got 4 times f of x minus 3 times h of x, all divided by g of x. So that is going to equal 28 minus 15 over 2. This is going to be 13 over 2. For b, we have h of x divided by f of x, and this is multiplied by 6 times g of x minus h of x. So this is equal to 5/7 times 12 minus 5. So that is going to be 5/7 times 7. 7 cancels out, and we end up with 5. And finally for c, we've got h of x, 5, times the square root of f of x, which is 7 plus 9, divided by g of x, which is 2 plus 2. So we get 5 times the square root of 16 over 4, which is 5 times the square root of 4, which is 5 times 2, and that is 10. And we've got our last problem here. Same thing, we've got f of x is -2, g of x is 4, and h of x is -1 for the limit as x approaches 3. So for a, we've got g of x plus 8 over f of x squared plus h of x. So this is equal to 12 over 5. For b, we've got 2 times f of x minus 5 times h of x divided by g of x times h of x plus 3. This is going to be -4 minus 5 over 7, so that is -9/7. And for our last question of the day, we've got g of x, 4 minus f of x, -2, times h of x, which is 1, and this is all multiplied by the square root of h of x, which is 1, plus 15. So we get 4 plus 2 is 6 times the square root of 16. So this is 6 times 4, which is 24.